This lab will see the motions of falling objects, which will include using these three equations. This first situation is that of the regular object falling at a regular speed. It is just a textbook being dropped from a certain height. As you can see, it tracked both its velocity at different time intervals. And here at the corner, we are mostly interested with both the time it took to hit the ground and how the velocity that it. The first computation model does not include the drag force. As you can see, the mass of the Powerade was 1.08862 kilograms, and it started from initial position of 0 and initial velocity of 0. Now, the only thing that would be affecting it would be gravity, which is just the mass of the actual Gatorade times the ground. The velocity just keeps adding based off the delta t times the gravity divided by its mass. And then the position update formula is just both the position of the Gatorade plus the new velocity times the change in time. As you can see, the graph over here to the right shows the Gatorade falling in a parabolic motion down, and as you can see, it apparently falls some negative 2.6 meters, which in this case is unrealistic because in reality it only fell negative 1.27 meters. Next computation model includes the drag force, which is basically just -1 times the velocity of the Gatorade times the coefficient love, which in this case is the magnitude of velocity and love because it's Valentine's Day, and B, which is the constant of drag. This will change the net force because now you have the drag force going up in the positive direction and gravity going down in the negative direction. Discovered by trial and error based off this graph over here that basically dictated how far it fell. And when it eventually reached that 1.27 meters, which was discovered and shown in the tracker function, then after doing that, one was able to discover the constant of drag because it's different for every single object and basically create this realistic prediction. The next object that was tracked was the slow mover object, which is a piece of paper, and this is the example of the piece of paper falling down. As you can see, it was oddly shaped, mostly due because, as you can see, the drag force played a significant role in this awkwardly slope. And as you can see, it was much slower than the Gatorade because the drag force, as you can see, played a larger role in this situation. The first computational model was that of the piece of paper that did not include the drag force. So in this case, just as in the previous examples, it just basically shows the force of gravity playing a significant role on the velocity and its position. And it lasted longer because in the tracker, it fell slower because the drag force played a larger role on the piece of paper. But in this case, we will ignore the drag force and just focus on the gravity force. The graph basically just describes what it would be like if only gravity was acting upon the paper. This dictates that it would have a velocity of negative 10.79. Second computation model, you can see that we now take into account the drag force. Now the only difference now is the net force now includes the drag force and the gravity force. This is very important in this case because the drag force is what played a huge role in how slow the piece of paper fell and how long it took, which is why the time is much longer. And as you can see, this now displays the more realistic speed due to including the drag force, which is close to negative 0.8. And then what this did in turn was we had to discover how much the drag force. Now, to answer the question if the slow-moving object would ever reach a terminal velocity, this answer would be true. The object reaches a terminal velocity because eventually the drag force will equal the gravitational force, which will cause a constant velocity. Now, to answer the second question, the object that was thrown down had a higher terminal velocity than the slow-moving object because due to the equation of the terminal velocity is equal to net force times the change in time plus its initial velocity. This is the case because the object that's dropped from rest only has the gravitational force and the drag force acting on it. While in the case of the object that's being thrown down, it contains both the force of gravity, the drag force, and the initial push that pushes it down, which just increases the net force. And the equation, the terminal velocity is equal to the net force times change in time plus initial velocity. You can see that the net force plays a high role. And if you increase the net force, then you would, in terms, increase the terminal velocity. And now, between the models of the objects that drop slowly, the model that contains the drag force in the model will produce a terminal velocity due to the fact that eventually the gravitational force and the drag force will balance each other.